Thanks a lot for being here all still in this wonderful conference, and thank you for this impressive organization. It's a very nice experience. So today I am talking about self-driving neural networks for yield curve modeling. And this is joint work with my co-authors Janneke van Brummelen, Julia Schaumburg, and Marcin Zamojski. So we start by the yield curve. So the yield curve, it shows the relationship between interest rates and the maturities of government bonds. So the yield curve is a very important object for monetary policy and financial markets because it gives an idea, it summarizes the growth expectations and inflation expectations and risk premia. So we're interested today in how can we forecast this. So typically the shape of the yield curve is upward sloping because it reflects the higher yield for longer maturities. But depending on changing economic expectations, it can even flatten or invert. And I've drawn down some extreme scenarios of this yield curve. And there's one with a high average yield curve, one with a very downward sloping yield curve, one with a very upward sloping, very steep yield curve, and one with a very low average yield curve. And all these scenarios are possible. And then I also made an animation, and we're going to try if it works now. And what I try to show here is that I have the current yield curve 1 year ago and 2 years ago. And we see that clearly it's a very smooth curve that we want to model. And also clearly there's a time lag in there. There's dependence over time, which also motivates that you can forecast something like this. So yeah, we are at the end. And what people have been trying till now to forecast this yield curve is a Nelson-Siegel model approach. And then my finance friends always find it nice when they start talking about this because they know this model. And why do they know this? Because it's a very useful model that can summarize the entire curve with just 3 components, which are level, slope, and curvature. And they like this because it's interpretable and simple to understand. But it also comes at a cost. So the problem is that by imposing this Nelson-Siegel structure, you have very strong idea about the functional shape of specifically the slope and curvature. And we want to be more flexible than this. So we contribute to this literature by learning the shape of the slope and curvature using neural networks. And we do this still within a factor model structure. So this is different from a fully fledged machine learning approach where you trade in the interpretability. And we don't do this. We have still an interpretable model, and we'll show you later how. But we go even one step further. So what you see is that this yield curve, it does not only move along 3 factors, it actually reshapes. And people have been trying to capture this reshaping curves with time-varying Nelson-Siegel models. And inspired by those ideas, we will also make our neural networks time-varying with observation-driven parameters. And this leads to the self-driving neural Nelson-Siegel model, which improves forecast performance for the US yield curve. So let's take one step back. The yield curve factor models. So we have a general framework of yield curve factor models here, where on the left-hand side we have our yields for each time to maturity tau. And it is built up as a factor loading matrix function, which produces our factor loading matrix, which gets as input the vector tau and is parameterized by gamma t. And we then multiply this times beta t, our factors, and in this work we only consider 3 factors, which is standard for Nelson-Siegel. So one specification of this model would be the Nelson-Siegel specification. I think plenty of you are familiar to this, but just to recapitulate is that the first column of this factor loading matrix function that is produced is the ones. And it will give us the level factor. And for the second one, the second column of our factor loading matrix is given by this exponential function, which gets as input the tau I, and is parameterized by just lambda, to give the full column for every time to maturity of our factor loading matrix. Then for the third column, which is for the curvature, it gives us the third column of our factor loading matrix by just this exponential function. And everything by just 1 parameter lambda. It's nice because it's interpretable, it's easy, but what if you want to be more flexible? So what we do is that we make a neural Nelson-Siegel model. So what we do is that we implement two tiny neural networks instead of these exponential functions. So we still, for the level factor, we don't do anything, it's still once. But for the slope factor, we replace the exponential function by a neural network, which just takes as input still the time to maturity, but now it's parameterized by gamma 1t. Then for the third column, which is the curvature, we get another neural network, still with input tau I, but now parameterized by another gamma 2t. And then I depicted here as well how our neural networks look like. So you get as input the time to maturity, then goes via 3 weights and 3 bias terms into the activation functions, and then it summarizes again with 3 weights to our entry of a factor loading matrix. So that means that we have 9 parameters, and we only consider here 3 hidden units in our neural network because it's already plenty to capture a wide range of different shapes of our slope factors and curvature factor loadings. So in total for 2 neural networks we have 18 parameters instead of 1 of this Nelson-Siegel model. So as I told you, we go further than this. So what we do is that we make this self-driving. So self-driving time-varying parameters. So we let the parameters of this neural network be driven by the gradient of the mean squared error. And although not applied to neural networks, a similar idea was proposed by Creel and co-authors in 2024. And people are maybe here familiar to this by the score-driven literature. So they propose it as a mean squared error, but in the score-driven literature we are used to taking the log likelihood. And then let updates of parameters be driven by a log likelihood. But we are driven, self-driven, by a mean squared error in this case. So the nice thing is that we don't have to assume any log likelihood function, and then hence also are more robust against some specifications of this likelihood function. But maybe some of you already have noticed that we have a bit of a problem here. So if we multiply our neural network times a factor, then the identification is lost, and therefore also any interpretability. So we have 2 goals in mind. We want identification of our factors specifically, and we want them to be interpretable. So similar to the Nelson-Siegel model, we want that our factors are still interpretable by the level, slope, and curvature. And we actually managed to transform the output of our neural networks by using a combination between anchoring and normalizing the factor loadings to fix the location and scale of this factor loading matrix. And therefore, and we show in the paper exactly how we do this, we can actually still interpret the factors as the same way as in Nelson-Siegel, as the level, slope, and curvature. Okay, now it will be the hardest slide of this presentation will come in the mathematical sense, because we are going to explain how we actually update our parameters. So please bear with me for a while or check in later. So we first have to initialize our parameters of the neural network and the factors. And then a data point enters, a t is 1. And how are we going to update based on this data? We want to incorporate this data in our factor loading parameters, but also in our factors. So we get a bit of a chicken and an egg problem, like which one do we do first, and what happens first, and how do we update them? So we decide to disentangle them and update them separately. So we do this for 1 until capital T, the full sample. And we do this in 2 steps. So we have an updating step, which incorporates the new data that enters. And then we have a prediction step, which tells us how our factor loading parameters and factors should be in the future, 1 step ahead. So the update step, we start by updating our neural network parameters, the factor loading function parameters. So we get our gamma t, and then we add a times nambla t, where nambla t is the gradient with respect to the mean squared error and tells us the direction in what way we have to move with our parameters to get lower squared error. And then A is a learning rate matrix actually, so it's small, and it will tell us in what size we should make this updating step. People are maybe familiar with this, with gradient descent or stochastic gradient descent. And then when we take this updated factor loading parameters, we put them again in our factor loading matrix function to get updated factor loading matrix. And then using this factor loading matrix, we can actually do a simple ordinary least squares regression in the cross-section of our yield curve to summarize the yield curve again in 3 factors, but now based on our produced factor loading matrix. And then we get this beta t given t. Okay, so we update it now. We take in the new data that comes in, and now we want to predict. So we define our factor loading parameters and the factors as autoregressive processes to predict into the future. And when we do this for one step, we get again our factor loading matrix, but now the predicted one, and then multiply them times beta to get a prediction of our yield curve one step ahead. But suppose now we want to do 8-step ahead forecasting. So what we can do is that we can repeatedly do this prediction step without updating in between to recursively obtain the 8-step ahead forecast. So for 8-step predicting, we get the 8-step ahead forecast. So we introduced a couple of new entities here, the A matrix, the B matrix, and the omegas. And we have to optimize those. So we do this by minimizing the mean squared error. And we have to impose some more restrictions because if you have 18 parameters in your neural network, you get quite large A and B matrices, 18 by 18. So that's a lot of time to optimize. So we do make a restriction that A and B need to be diagonal for the neural network. And then if you impose the restriction that A and B gamma are equal to 0, then the neural Nelson-Siegel model will be just its static form. And then we add one extra thing, which is the scaling of the gradients. And we do this because it's kind of common thing to do in the gas literature. But we scale with an adaptive second moment scheme. And this is quite standard in neural network literature. Maybe people have heard from Adam or RMS prop. And this is also a way what we implement in our model, in our filter, to be more robust. And we denote this by scaled self-driving neural Nelson-Siegel model. And in the paper is more about how we do this exactly. Okay, we go now to the application to actually see whether it makes sense to see if we have better forecast results. So what we do is that we have yield curve data by Liu and Wu. And we have actually a set of 1 till 180, and for a shorter part of the sample till 360 maturities. But we take out 24 of those maturities to train our models. And we overweight the earlier maturities, and we include maturities until the 180th maturity. And then we forecast 1 till 12 months ahead. We have an in-sample of 1985 till 2004, and an out-sample of 2004 till 2024. Well, first we have a look. So we first estimate the model on the full sample, so 1985 till the end of 2024, to get a bit of an idea what is happening in sample. And we have a look at the factor loading matrix of the SSD and NS model. And this picture depicts the factor loading column, the factor loading matrix column of the slope factor. And we anchor on the earliest maturity on the left-hand side to 1, and on the right-hand side to 0. And in between, we let the neural networks tell us how the factor loading matrix, this column of the factor loading matrix, should change over time. But actually, you see, there's not a lot of movement happening here. However, if we now have a look at the curvature factor loadings, we see that there is a much more happening over here. There's a lot more movement. It's quite hard to actually make a nice figure out of this, but you have to trust me that what's happening is that the peak of the factor loadings is moving from maybe higher maturities to lower maturities and then back. And this is actually contributing to better forecasting results. Because if we look here at the relative root mean squared error plot, where we compare to a random walk, and what we do is that we have some benchmarks, the random walk model, the Nelson-Siegel model, and the neural Nelson-Siegel model. And then we introduce a new benchmark, which is the scaled self-driving Nelson-Siegel model, where lambda is now evolving in the same way, updating in the same way as the parameters of our neural network were updating. So the same filtering procedure is now also done for Nelson-Siegel, and we do this to actually distillate whether it's the neural network that's contributing to our result or the self-driving dynamics. And then what we see on average over these 6 maturities out of the 24 that I've selected, that the SSD NNS has the lowest forecast error and is significantly outperforming the random walk. And here the SSD NS is also outperforming random walk, but the static models are not. So we see that the self-driving dynamics, they contribute here to better forecasting results for the 1 month ahead forecast horizon. And when we dive deeper into these results, we see that especially for the curvature forecast results, which is more like the medium-term maturity, so let's say the 60th maturity, we see the only model where we cannot distinguish the forecast with the random walk, while the other models do significantly worse. And then we add another model, which is an ensemble between this SSD-NS and the SSD-NNS model. And this actually is improving forecasts a little bit, but it's still very close to the SSD-NNS, being kind of an extra argument for our model. Then we go to the 12-month ahead forecast horizon. So a bit further. And what we see here is that still the SSD-NNS has the lowest forecast error. But now, interestingly, also the neural Nelson-Siegel model is doing very well and significantly outperforming random walk, where the NS variants, the Nelson-Siegel variants, are not. And including the SSD dynamics still gives us a bit of an extra edge, but the neural Nelson-Siegel part is here the most contributing to the forecast results. And even the SSD-NNS is better than the ensemble between the 2 models. So then we have a look at how the error accumulates over time to get a better idea on what is the error distribution for the different type of maturities. And we do this for 2 horizons and 3 maturities. And we see especially for the shorter maturities, there's a lot of the error accumulating during the financial crisis and the COVID periods. But that's also where our models actually gain their comparative advantage over the other models. So the Vrije SSD NNS is specifically doing well in those periods. And however, although this is not as visible in the higher maturities, also there the comparative advantage is gained during those times. Well, then we have a bit of a larger plot, but what we do is that we have a multi-horizon model confidence set based on the average superior predictability. So what we do is we have a look at one maturity, and they want to know what is the best forecasting models. And then we create a model confidence set, where we kick out models of this set that are significantly performing worse forecasts for all the horizons on average. So we consider the 12 horizons here. So if it's green, it's included. If it's white, it's excluded. And you see that we introduce a couple more models here. And specifically, we have now 3 variants of the SSD NNS model, where the 3 SSD is the one that I also showed in previous tables. But with the 1 and the 2, I impose some more parameters sharing the A and B matrices to kind of speed up the training process. But actually, the most flexible variant here, the 3 SSD NNS, is the one that is always included in the model confidence set, while other models are excluded for at least 4 of the periods. And specifically in those area in the maturities that relate to the curvature of the yield curve. So then we do actually something new, which is quite interesting, is that we take the same test by Quadfleek, but we now change kind of the dimension. So instead of looking per maturity, we now look per horizon over all the maturities on average and see which models are included in the model confidence set. And what we see here, yet again, the 3 SSD NNS is always included in the model confidence set, where other models are not, except then for this SSD ensemble, but which actually consists out of our model, right? And also to stress here, like the Nelson-Siegel models, the self-driving ones, they are always excluded of the model confidence set, showing that our model always is better than Nelson-Siegel, the self-driving one. So in the paper, we have a bit more. So in the paper, and I don't have time to go over everything in detail, but to summarize is we have a closer look at the in-sample results. So what we do is that we compare the Nelson-Siegel model with the neural Nelson-Siegel model, the static ones, and then have a look at the factors they produce and the factor loadings. What we actually see is that with our neural Nelson-Siegel model, because of the strong, the hard restrictions we put in there, the constraints, we actually gain more interpretability of our factors. And then we also have a closer look at the curvature loadings. And what we see for the 3SSD NNS model is that we shift the maximum of the curvature loading from the higher maturities to the shorter maturities in 2024. So it means that actually most of the explainability about this curvature is first at very long maturities, but actually can move towards the very short maturities. And that's producing the better forecast results. And also motivating why we need actually this changing curvature. So then we also do a factor analysis where we compare the produced factors we get with the empirical proxies. And the problem is that these proxies, they are static type of proxies. So we see actually our model aligns very well with those in the level and slope, but in the curvature, it does not. But it's actually because the static proxy does not capture this time-varying kind of curvature in the yield curve. And then we do also an extreme scenario analysis where we look at the places where we get the highest forecast error. And we see actually there specifically that our model captures the shape and the update a lot better than what the Nelson-Siegel model can do. And then we also add a simulation study. And to summarize, what we do is that we have a dynamic Nelson-Siegel model which we estimate on the full sample and then simulate from this model. And therefore it's empirically calibrated, but this is a static model. But then we replace the lambda in the Nelson-Siegel model with time-varying paths. And these time-varying paths, we impose the structure ourselves, and hopefully it can tell us something about reality. So we have an AR1 dynamics, and we have one with structural breaks, and we have empirically estimated lambda paths. And this way we can really stress test our neural network model compared to this Nelson-Siegel models, because we are here in a scenario where it really favors Nelson-Siegel models, since the simulation experiment is formulated as a Nelson-Siegel framework. We do this for 3 sample sizes, and we see actually that our SSD-NNS model is very competitive with this SSD-NS model, and even sometimes outperforms, and specifically when there is a lot of time variation happening. So to conclude, what we do is that we show that we have flexibility of neural networks, improve the capturing of the yield curve, and specifically for the longer horizons. And then adding the self-driving dynamics improves forecasting, specifically because it captures the moving curvature a lot better, contributing to the better forecast results also for the shorter horizon. We are among the best forecasting models across all horizons and all maturities for the benchmarks we included here. And some exciting thing to think about even more is that this structure of imposing these neural networks within this type of factor model, which we then could call a neural factor model, could also be used in other kind of term structure applications, but even other multivariate time series applications where you assume or expect that there is some kind of smooth relationship between your time series that you can capture with this neural network in potentially a time-varying way. Thank you, and that was it.
Thank you. And the paper will be discussed by Sarah Mouabbi from the Banque de France.
So thank you very much for having me here today. I very much enjoyed reading Sicco's paper. And sorry, I just located this. Perfect. So I will briefly specify the main elements of the paper that I think are worth taking with you. And then I'm going to be giving a bit of an overview of the literature so that we can position it a bit better and place it in the literature. So the model itself, so the framework, is a factor model of the yield curve, where the interpretation of the factors will preserve the level, slope, and curvature interpretation. The idea is that the first factor, the level, essentially loads on all maturities, the slope is downward sloping, so it loads more on short-term maturities than long-term maturities. And then the curvature is going to be loading predominantly. The medium-term maturities will be loading predominantly on this third factor. What is happening here is that there is a replacement of these fixed loadings, which is what we usually have in a traditional term structure model. And now this will be replaced with time-varying ones through a shallow neural network. So the neural network itself doesn't need to be deep. You don't need to have a lot of layers. It's shallow, and it seems to be sufficient, and it does the trick. Now, the reason why the authors argue they present this framework is because they want to preserve the interpretability of these factors, and they will therefore introduce identification restrictions on the loadings such that you can uniquely identify them and preserve the level, slope, and curvature interpretation. Now, the main findings are that their models, they have a sequence of models, as you've seen, but the most sophisticated one, the one that is self-driving and embeds the neural network and the Nelson-Siegel interpretation, this very model is the one that seems to outperform standard benchmarks. So you'll have the random walk there, the Nelson-Siegel. They won't have the Diebold and lead. It could be something that you might want to incorporate. And it will be able to outperform them on average and uniformly across maturities. And so this is going to be an element I'm going to be talking about later on in my discussion. The strongest gains are at a short forecast horizon and at medium maturities. And I think that this is key. This medium-term maturity might be fully captured by the curvature changes that Sicco showed earlier. Remember, those are the ones that load predominantly on the third factor. Now, the literature as it stands, and maybe my representation is going to be extremely schematic, goes as follows. You have several purposes for these term structure models. You might just want to fit the yield curve. In fact, the data that Sicco uses comes from a fitted yield curve, which falls into the second category, the non-parametric category, the Liu and Wu paper. But the original term structure models first started with parametric curve fitting, and this is where your standard Nelson-Siegel falls into place. You have a functional form for yields across maturities, and the idea is to have a small set of interpretable factors. Then we moved on to more flexible approaches, splines, kernels, even machine learning at this point. And then you have a second segment of the literature that is interested in forecasting. So we go beyond fitting now, and we care about predictive ability. And so the most common ones are the random walk and the Nelson-Siegel model. But here I would invite you to also look at more recent papers. I'm only going to cite one off the top of my head by Laura Coroneo and co-authors, which introduce surveys and show that it adds into the predictive ability. And so within this forecasting strand of the literature, you will see that you have time-varying parameters showing up, machine learning papers, and neural networks in particular that are becoming more prevalent in this strand. I'll be quicker on the second part, but I want to focus on my top point, which is the no arbitrage asset pricing models. Now, these models are trying to serve a deeper purpose. It's not only fitting, it's not forecasting, it's a deeper economic interpretation that we're trying to extrapolate by introducing a consistency across maturities. So this no arbitrage condition imposes that every maturity is intertwined with the other. And this allows you to link yields to risk factors and to decompose your interest rates into an expectation and into a premium component, okay? You have an additional contributions to the literature, how to address the zero lower bound, how can you incorporate stochastic volatility, whether factors should be spanned or unspanned, what are the hidden factors, in other words, in the yield curve. I'm going to just omit that, but what I want to say is that your paper at least falls into all three categories. So you have a hybrid framework, and I think it would be useful for the reader for you to emphasize that. Now, I'm going to start with my first comments. What I want to do is I want to better understand the role of your key ingredients. And your key ingredients are twofold. You have your factors and your loadings. Your factors, you've made quite a strong effort. Actually, it was a valiant effort. It's very difficult what you did to preserve the identification restrictions that give you the interpretation of level, slope, and curvature. And what I will argue is that if it's a forecasting paper, of course the level, slope, and curvature gives you a summary, it might be useful, but ultimately what you care about is your ability to forecast. And maybe you've tied your hands more than you need to. So I wonder, all of the models that you have, you're benchmarking always against models that have a Nelson-Siegel structure. And I would invite you to just let go of it and let's see, would it improve or not? And if it improves, that's a finding. And if it doesn't, it's also a finding. It means that this Nelson-Siegel interpretation is not for nothing that we've been dragging it along across the years from the 1980s. It's because it has some importance. So that's my first recommendation. Another recommendation is to better understand how important is the time variation in your loadings. So, of course, when you have your shallow neural network, but it's not there that the gains are coming from. It comes from the self-driving nature, as far as I've understood from the comparisons you make. But we also notice that if you have too much time variation, then you have a problem. There's a picture you didn't show, but that is on your paper, figure 7, and we can see that if you have excessive time variation in your loadings, then your forecasting performance weakens. So what is this sweet spot in time variation that is necessary? So I would invite you to dig a bit more deeply into that. The second point I have is that, as I mentioned earlier, it is a hybrid framework. It's a framework that falls into at least 3 of the many strands of the literature. But what I'm going to try and argue is that perhaps, based on some preliminary results we've seen today, maybe it can actually fit 4 of these strands of the literature. So let me be a bit more explicit in what I mean. So the model outperforms on average, but it also outperforms uniformly across maturities. And this means that these typical no arbitrage conditions we impose to have consistency across maturities might be coming at a low cost for you, because you seem to be complying to some consistency across maturities without even imposing it. And I wonder if you were to actually go all the way to impose these restrictions, if your forecasting ability would survive. And if it did survive, then you would have what I think a central banker would adore to have in their hands, because then you would have true economic interpretation. You would be able to decompose through forecasting expectations and premia, and that becomes much more useful for a central banker. I understand that I'm running out of time, so I'm going to just skim through the last bit. So I think that you can even exploit the full potential of your model by starting your data even earlier. You don't need to be restricted by the grade moderation, because you have a model that it is designed to be able to tackle these changes in regimes. I would encourage you to do a little bit more of a focus on what happens around the zero lower bound in your setup. And I would want to know whether the curvature, the maximum maturity of your curvature, you say it decreases over time and reaches up to 12 months in 2024. And I would want to know when the biggest fall happens. And if it happens after the zero lower bound period, I think that this is something that needs to be looked into more carefully. It can be a very interesting feature. So I'm gonna stop here in the interest of time, but what I wanna say is that the results speak for themselves. The forecasting performance is there. And what I would encourage you to do is to better understand the source of your success, essentially. Thank you very much.
So I guess, Sicco, you want to reply?
Yeah, thanks a lot for also pointing out to maybe draw an even bigger perspective in how we can use these models. I think it's very helpful and also very interesting to see how we can maybe stress test even more and like include more benchmarks maybe, and then see if the results even hold up over there. One comment I wanted to make is that in these factor models, we always have the bit of an issue that to have any identification, we have to put in some restrictions somewhere. And some people put it on the factors, and some people put it in the factor loadings. We now put all our restrictions on the factor loadings. And yeah, it could be that is actually hurting forecasts somewhere. But you have to make a choice over there.
Absolutely.
Yeah, thank you.
Okay, thank you. I wasn't sure whether the AI agent would stay with us until the last session, but apparently it does. So please go ahead.
Yeah, still here. Looking beyond US Treasuries, how easily can the framework be extended to euro area data with multiple sovereign curves, segmentation, and credit risk, and to joint modeling of yields with macro variables relevant for policy like inflation, output, and other financial conditions?
Yeah, thanks a lot, AI, for the beautiful question. I think it can easily be extended to other European countries and their yield curves. And it's also very interesting to see whether we can include other macro variables. And more importantly, actually, these neural networks, they don't only allow for maybe a maturity as input, but maybe we could even put macro information into the factor loadings by inputting it into the neural networks. And I think that would also be a very interesting idea to do.
Okay, any more questions from the audience?
Thank you for this very nice presentation, Bernd Schwab from the ECB. So it seems like when the lambda becomes time varying, that arbitrage freeness goes out of the window and that there's very little one can do about it. But still, even if the model is not arbitrage free, it would still be interesting to look at the term premia that are implied by the model. So to decompose any maturity into expected future short-term rates and a narrow term premium, and just to look at whether the sequence of models has vastly different implications for the term premium, or whether they don't really matter because we mostly make the measurement equation of the models more flexible. And so this is more a comment than a question. And a question is, so the dynamic Nelson-Siegel is a model in state space form, and the measurement equation is now more flexible. The factors evolve over time, and they have variances, state equation error variances, whether one can also use this to make these variances time varying in a self-driving way, and whether that is sensible. Thank you.
Do you want to reply immediately to that? And then
yeah, so like the reason why we kind of focus now on just Nelson-Siegel, not dynamic Nelson-Siegel, actually our forecast results were a bit better for Nelson-Siegel than dynamic Nelson-Siegel. But I think it could be very interesting to also look at whether we can make this variance time varying, because we saw already like adding second moment information about the parameters of the neural networks makes it more robust, but also to look at the mean squared error itself and also impose there like the variance structure and make it time varying. I think it's a good idea to do. Yeah.
I think Faizan had a question.
Thanks so much, Sicco. I had a question similar to the AI, but not euro area specific, which is, yields are available for a wide range of emerging market and developing economies, but precisely that's where the yield movements and predictability can be important, because the yield changes are real sign of, they can move very rapidly, and that can be a sign of underlying distress. So what assumptions are needed if on how well the yield curve needs, how deep the financial markets need to be for the model to work well? Could you extend it to countries where there is a yield curve, but it's not very tradable, it's not a very tradable treasury market?
So for now, we use this data set by Liu and Wu. And the nice thing is that there's no missing information there because they already imposed that. But potentially that could also make they still do some imputation there. So it's a bit of the question whether that is still possible in those, and how good this imputations would be for smaller countries. But it would be definitely interesting if we can still impute that, whether we can still use it in our model. And what is nice, and why we use this kind of factor structure, that still, if we estimate the model on a selected number of factors, we can still make forecasts also for other time to maturity. So we don't need all the maturities that Liu and we will create. So that I see possibilities there as well. Yeah, thank you.
So now that we know that allowing for this observation-driven time variation seems to improve the forecast, I guess one could also try to use then this setup that seems superior to others to answer economic questions. So for example, one that comes to mind is that it seems that the inversion of the yield curve is not as informative anymore about recessions as it used to be. And maybe you can exploit the structure that you have created to see what's going on now when the yield curve inverts. Why is not anymore as representative of economic activity as it used to be in the past? But there are certainly others.
Yeah, thank you. I've seen also things about that, and I agree that it could be interesting to see whether this factors, what kind of interpretation and what kind of predictability do these factors, for example, also have on these kind of economic applications. Yeah, thank you.
Are there any other questions? If not, then let's thank Sicco and Sarah for the excellent presentation.